Mine is different.
You want to do a little exercise, live exercise, where you put those markdown files, the slides, into the OHBM 2018 GitHub repo so that people can have the slides and then clone the report.
But those are reveal.
It's really big, the JS.
Well, it requires, so this repository is with submodule setup and everything. It's just overkill. Well, I can do it, but no. Well, I have a different image. It still works. No. That's my checksum of the FCL image.
Okay, so
there are many good versions.
we probably need to reconvene. So Dorota, you're first, and then Michael. Is that right? You don't know?
Yes.
Yeah. Okay. So, and Dorota, you'll be finishing the section 2 with the reproducible basics, right?
I mean, this is part of section 3, I guess.
Section 3. Okay. So it's already section 3.
But it's here in section 2. Yeah, kind of.
So let's start again. Thank you for coming back. I see that the courageous ones are still here. Good. Okay. So how much time are we? I think we should start slowly, but I mean, I guess we can wait a few minutes more, just in case. Do we see? Yeah, we see a few empty computers. So, yeah, we can. Yeah. Okay. Let's wait for the people to come back. Okay. Meanwhile. How's the jet lag? Everyone. I see. Dave's jet lag is really bad. You good? Yeah, we need coffee. We need coffee. There's a break. I think there's a coffee break at 2. So
I think that's all, yeah.
you know. So if we're getting to miss the coffee break, someone please just raise your hand. Say, hey, coffee break is at 2. We should stop for the coffee break. Okay, I think I'm not sure we can wait much more for the couple of people that are a bit late. So hopefully we'll get them to sort of like a catch up. So Dorota, I think we should start.
We'll start from the same page as Jarek was pointing you to. So does anyone know how to get here? Who doesn't have this page? Okay. So the third part, it's ReproEnv. If you click on this, and you can go to presentation. I mean, for presentation, you don't have to follow exactly. For exercises, you might want to have this open for like copy and pasting. Okay. So before lunch, Jarek was talking about GitHub and Data Lab. So for me, these tools are like tools that you can use for controlling your code, like Git, and controlling your data, like Data Lab. So now I'll be talking about like container-based environments, and this you can think about like tools that can allows you to control your environments. So what are the container technologies? So basically, the main idea is that they isolate the computing environments, and they allow to encapsulate the environments in self-contained units. So why do we need these containers? So because we're at the reproducibility workshop, the first and most important things for us is the science reproducibility. So basically, because every single project depends on not only on the code and data, but also on the computational environment. Containers allow to encapsulate this environment, so every single person can later try to recreate your work. But for something, if you don't think that is good enough motivation, I will give you some few smaller motivation that you might want to use right away. So first of all, collaborating with your colleagues. So you might often ask other people for help, and it's much easier to get help if other people are able to recreate your problem. So containers, as we're saying, can encapsulate your environment, so you can easily share this with other colleagues. The second motivation is that you often, especially in neuroimaging, you might start your workflow on your personal laptop and just run for one subject. But sooner or later, you might have to change the hardware. And if you don't use containers, you would have to repeat entire installation process once again on different hardware. And you might have to do it a few times during your PhD or postdoc time. The third one is especially was important to me. So I think many scientists are uncomfortable installing software. So maybe I can ask how many people are uncomfortable installing software? Everyone is comfortable? Huh? Okay, so I personally don't think it's so much. I mean, it's kind of fun, but I was always scared. So basically, I think for me, it might be hard to believe that installing one more software would solve the problem. But for me, it's having for example, container technologies, Docker technologies, allows you to experiment in kind of safe environment. So whenever you need, you can switch to your default environment and you can remove it. So I think it's very useful for this, for learning purposes as well. And the last one is if you are lucky, you might not have to even install things because they might already exist. So for example, like for this tutorial, we didn't ask you to install all of the like software that we are using. We only use like we prepared a virtual like machine, and you are using everything inside. And because we'll be using like mostly during this presentation Docker, Docker Hub is also like excellent place to find existing images. So, so for those who are like, so you already have some experience with working with virtual like with containers because you are using virtual machine right now. So basically, like, so you know that like it's basically like use the same hardware, obviously, because it's only like on your laptop, but it has like independent user space and software, and so basically like you don't have like so easy access to what is on your computer, but you can always make some additional like mounting points to share, for example, like directories or ports. And we'll be practicing this later. So tools. So there are two main types of virtual containers. First is called virtual machine, and this is what we are using today. So that's the main virtual machine you are using right now. But there are also like containers type containers, yeah. And the most common is Docker, but during this tutorial we'll be also using Singularity. So the main idea is the same, is to isolate the computing environments so that you can later generate the environments and you can easily share the environment. So the main difference between virtual machine and containers, so on the left side you have like scheme of like virtual machine, on the right Docker type Docker container. So basically a virtual machine has to emulate entire computer, software and hardware, and it's using hypervisor to share and manage hardware. And guest machines are completely isolated and have dedicated resources. So for containers like Docker, they share the host system's kernel. They still have isolated user space, and they have independent beans and libraries, but they are much lightweight and they are much faster to start. So like if you wanna like choose the technology that is good for you, it might depend on many different things. So first of all, like it's the hardware is available to you. So you might have access to hardware that is already like designed to use specific virtual machines or containers. The other aspect is important to think where is your data. And for now, probably Docker might be the most portable technology right now. The reason why we're not using Docker for this tutorial as a main container is like there are some installation issue for like Windows, mostly for Windows, and that's why we decided to use virtual machine. But we have exercises using Docker inside the virtual machine, and we will be also using Singularity because many HPC centers do not allow to install Docker inside. So yes, as I said, like Docker is the most well-known container technology probably right now, but the problem is that can escalate privileges, and that's why HPC centers do not support this. So what is also good about Docker, like if you have Windows Pro and Mac OS X, you don't have to install a virtual machine anymore. If you have Windows Home, you still have to install it. No, you don't have to install it. It works, yeah. So, and also like Singularity, for like both for Windows and Mac, you have to install a virtual machine. It only works on Linux. So it's designed for a scientific application, and it's supported in many HPC centers. So the good thing about like Singularity is also that you can use Docker images with Singularity. Okay, so that was my introduction, and now we will have like hands-on session. So if you go back to the main page, you might want to open exercises because it might be easier to copy-paste some of the like longer commands. So does anyone have a question regarding introduction? No. Okay. So
thank you. Quick question. So to understand a little better, Docker, you can create a Docker in Linux and take that and bring it in Windows and it will work? Or
I think the mic doesn't work, but oh, okay, sorry.
all right, it just need to wake up. If we create a Docker in Linux, can I take that and use it on Windows?
Yes, but like so if you are creating like new operating system using Docker, I mean it's only you can only create Linux-based systems. So you can have like Docker images based on Ubuntu or Debian. You cannot have Docker image for Windows or for OS X, but you can use it everywhere. I don't know if that's... So one thing is like what type of system...
So, but basically, if that person has a virtual box on the machine, then you could use that. So you would have a Linux-based system on your Windows machine.
I mean,
you would use the.
But that was about Docker.
Yes. But
So,
then, yeah.
sorry, maybe I'm confused.
No, I think you're right that the Docker image can be brought over to Windows as long as you have Docker installed on Windows and reused.
But inside the Docker container, you can only have Linux type environment. Yeah. So for example, for a virtual machine, you can have like Windows virtual machine. It's not possible with Docker, but I'm not sure. Okay. So I have like two exercises. One will be like creating Docker image with FSL and Python. And the second will be like I will concentrate more on using this Docker container. So, okay, so in order to have like a Docker container, you have to first create image, what is called like Docker image. And the way to build a Docker image, you have to create a text file that has that is called Dockerfile. So basically, Dockerfile contains all instruction. What do you wanna install within Docker container, and what do you wanna run within Docker container right away? So the simplest Dockerfile might look like this. So basically, you always start from some base image. As I said, it's always some kind of Linux, so it might be Debian, it might be Ubuntu, like in this case. And you run, and later you ask for software to install. So in this case, I was using apt-get to install Git and Emacs. But if you have like more requirements, if you want to install, for example, FSL, the Dockerfile might look like this. It also might be much longer. So basically, like Dockerfile might get complicated, especially if you are using like various software. So that's why today I would encourage you to use NeuroDocker. So basically, NeuroDocker allows you to generate Dockerfile or Singularity file for neuroimaging software. So if you go to NeuroDocker website, sorry? You can click on NeuroDocker. So here's the list of software that is currently supported. So you can see you have like neuroimaging software like AFNI, ANS. You also have like more general software like Python, and yeah. So today we'll be using NeuroDocker. So as I said, it can simplify the creating of Dockerfile, and it also incorporates the best practice for installation. So your image is not bigger than it has to be. And yes, it also can use Reproducible that Satra, I believe, will be talking about. Will you? Okay. For minifying existing Docker images. So basically, like the same Dockerfile using NeuroDocker. So can be created using NeuroDocker by typing this command. So that's what we'll be doing like as our first exercise. So I wanna to build like new Docker image that has FSL inside. So here, as maybe one thing that I wanna mention, like with NeuroDocker, you can install FSL directly from FSL website. This command is a bit like longer because we're using we're installing FSL from NeuroDebian, so it actually like it might be much smaller. This is only for 509 if that's important to you. Okay, so I will go now to our virtual machine. Okay. What was it? Okay. So everyone should be in section 2. So if you don't know how to get there, it's source activate section 2. If you are in section 2, you should already have this in your prompt. Okay, so if you are in section 2, if you are in the home directory, just in case, you can type cd tilde. And we'll create a new directory, so you can type mkdir. And we will change our directory to go there. You can use tab as Jarek was pointing you to. And we will, and this is the place you might want to copy paste the command. So once you are within this directory, you can copy paste the Docker run command to create Dockerfile. Oh, okay. So who has problem with copy pasting? Anyone?
So remember, especially you Mac users, remember that the keyboard shortcut you often use on the Mac has the command, whereas on the paste in your virtual machine uses the control. So watch carefully which the right pasting and copying are for the different machines from your one to the other.
So you can copy whatever you are copying usually, and once you are in terminal in virtual machine, you just can click on the right side of your touch pad and just use paste. Okay, so this is like pretty quick. So right now we only created Dockerfile, so you can check this that it exists in your directory. You can also cut this Dockerfile, and you can see that it's much longer than the command itself. So this is only Docker files. This is like text file. We didn't create any image yet. So in order to create Docker image, we have to type Docker build, and it's -t, and this is where the name of your image you are creating goes. So I was using my FSL, and this is the name that I will be using in example. So you can choose whichever name you want, but you would have to change this later. And what is important is dot at the end. So one thing that I forgot to mention that when Docker is built-in image. It has layers. So you see in this example we have like 8 layers. And every single layers is for like installing like different things or running different commands. So one thing that is like, is anyone still waiting for this? No.
Can you show the history of the commands just to make sure everyone has
So you can actually go to my presentation to have history here. So one reason why it was like, so this, we were installing FSL, so you might wonder why it was so fast. So because I didn't want to wait too long, I was cheating a bit. So this image actually exactly the same image already existed in your virtual machine. So this is actually also like nice thing about Docker. So it has layers, and it only changes layers that you don't have on your computer. Because we had all layers already installed, that was fast. It can just reuse the same layers for different image. So if you want to check if you have this image, you can type Docker images. And okay, I was checking many things before, so you shouldn't have as many images as I have. Yeah, but if you can see I have like my FSL here. Okay, so sorry. So that was the image that you. Okay, so this is the way how we create image using Docker image using NeuroDocker, and there's like similar command for Singularity if you didn't want to use Docker but Singularity. The NeuroDocker command is very similar. For building the image itself, you to use sudo singularity build, but I don't want you to do it now. You already have this image on your computer. So what I want you to do is like creating new image. So as I pointed you have you can go to NeuroDocker website, and here you will go directly to examples. So here you have like all list of examples of how to create Docker files for different software. So I want you to add. Here's the example. I want you to add to our existing command to our existing image Python. So you already have this. No, this is Singularity. Sorry. You already were using this command to create Docker file. And I want you to try to add Python to this installation based on the help from our website, from NeuroDocker website. So for those who are not familiar with Python, you were using like miniconta, so you should search for miniconta keyword. And I can give you like 4 minutes. How much time do I have? Is it the first one?
Yes.
What happened? You had newer file.
use the mic if possible.
Yes. So I think for people who downloaded the files recently, because I was using the latest version of NeuroDocker. The latest version of NeuroDocker has changed, and that's how it's. Yeah, I think so.
Do you think we should have used the container to?
No, you should just wait.
So one of the things that is important is the version of these tools that you're using. So the reason it's rerunning is because the version of the underlying container has updated, and it was referred to by the latest version. And that's, I think, something that's quite important in the context of reproducibility, that you want to use a very specific version so that you can re-execute it in the same way.
So for here, I actually was not using, so that's. Although I don't know because, okay, I don't.
Where did we define that version?
Once again, oh, okay. So in this case, I will define here. So if you go, maybe I will go like, I mentioned Docker Hub. So let's, for example, go to Ubuntu. So you see that this is like official repository for Ubuntu, and for many for many images, you will have also tags here, and you have different tags. So if you wanna later use this specific version of Ubuntu image, you have to add. Sorry. So here, for example, like Docker pull Ubuntu. Sorry. Instead of just using Docker pull Ubuntu, that's the way how you download the images. You would have like 1604. Is that the way? Is that the version? One of? Yeah. For example, this one. So you have the name of the image, and you have comma, and you can add tag. If you are not using any tag, if you don't specify tag, it would take the latest. And that's the problem with latest, like Satra was mentioning.
So that tag is still not going to give you a precise version, because as they update 1604, they just keep updating that. So you can see that
Really?
all of those images were updated 11 days ago.
Okay.
Right? So as they apply security updates. However, Xenial 2018-05-25 is a much more fixed version of Ubuntu. Now,
Okay.
all of these are kind of things that you have to think about. For some cases, the latest might be fine. But if you were to do reproducible thing and you were to put this container out there saying, I want to use this container 2 years from now, and I don't want to be pulling the latest version of Ubuntu when I build that container, then you should tag it with a very specific version that's available.
So a single point of failure is Docker Hub, and so how do we? So do we have to trust that they will always have the images available?
No. You will discover later on. This is pretty much the problem which we kept preaching about, because even here, those tags change, so you don't have guarantee that what you're using is actually what you were using before, if you say latest, right? And then Docker Hub is gone, everything is gone, right? And Docker Hub is the point of exchange. But we could keep those images within version control system. Annex allows us to put arbitrarily big files into version control system, right? And associate information where they're available from. So at the beginning, we could associate, they come from, let's say, Singularity Hub or Docker Hub. And if they're gone from Singularity Hub or Docker Hub doesn't exist, at least somebody like you might have that image, and you maintain information that you have those images available somewhere. And then you could fetch it, you could share it again on some, Dropbox, right? While your Git Annex repository will maintain information where they are available from. So that's our solution to the problem that those images indeed could be gone, they could be changed, even though tag will stay the same, it might be different image. But version control systems are cool, or content trackers are cool, right? And they allow you to maintain information about their origins.
So
I guess you could always have the tag having the exact hash or something that and then verify that the tag is actually the right.
Okay, so I'm still waiting for the build. Okay, so who installed Python within? the image. Do we have any success? So I think I don't really have time to do it now, but so basically, if you want to install Python, you would use miniconda, and so it would be like very similar lines like this. But if you want to have like only Python without like extra packages, you just remove NumPy, pandas, iterates. But now, I don't want to do it now because I think we don't have time. But you can check just images you already have. So hopefully everyone has myFSL. If you don't have myFSL, at least you should have FSL. So you can always, like for the rest of my tutorial, you can use FSL if you were not able to use to build myFSL. Okay. So once we have this image, we can run a Docker container. So the simplest command to run a container is just docker run. So you can type docker run myFSL. And you see that actually nothing happened because, because basically this command only runs. We don't have any commands within the image. So basically it created a container and it just left. And we didn't ask for anything. So that's kind of like, that's why we didn't have any output and nothing interesting happened. So to do something more interesting, we can, because we install FSL, we can try to run now bet. So maybe first you can see that if you just type bet, we don't have bet in our virtual machine. So, but it should be in your Docker image. So we can type docker run myFSL bet. And you see now that actually what happened is that now you ask for a specific command. So the bet was run within the container and the standard output was printed in our virtual machine. So now you can use actually like try to run this bet on like using one of the T1 images that we had. So I believe already, so I forgot to update this. So we will use, because already Jarek asked you to install this data set, so I don't want to do it once again. So the only thing you can, so don't create a data file because you already have this data set. So you should have, if you type, you should go to your home directory and you can check the content. So you should have, where is it? DS, this directory. But I believe you didn't download any single image. Any single image, any single file. So now you can use data.get to actually download the content of the file. So we'll be using only one file. So that's also like very nice about data.lot, that you install entire like repository, but you can only download one file. So we'll be downloading this T1. And you see this is like the time, the moment that data.lot is actually downloading anything. So as I said at the very beginning, there's like, this is like your container and your host machine. So kind of now the virtual machine is kind of host machine for Docker. So you are not sharing any directories, any resources. So now if you want to use the file that exists on your virtual machine, on your host system, you can mount this directory. So you can type docker run, And here's the new things that we use. So we're using -b, and we remount the, yes. You can also copy-paste from the slides. So you remount the directory from the virtual machine, so from the host system to the Docker. And within Docker, we'll be using data as the name of the directory. And you can use bet. And maybe we can actually copy-paste the rest of the command because I don't remember. Again. Okay. So here, like, once again, oh no. So here is once again, so we are running again bet within our container, but this time we're using -v option to mount the directory. So we'll be mounting our directory that is called DS000114 to the directory within the container that is called data. So that's why, oh, now I'm missing the name of the image, my FSL. FSL. And now we are running bet command. So the bet command takes the name of the input and the name of the output. So here we'll be using, this is the path to our input. So as you can see, we have to use the path from the container. That's why you don't have DS000114, but you have the data. And you can run it. So now it takes time because actually like you're using bet. Okay. So you can see if anything happened, and if you check the content of your directory, you will see that nothing was created, because actually what happened was like we only mounted. Oh, okay. We already mounted one. Where is it? One directory. So we only mounted the input, but still like the output stays within the container. So we didn't point it to output directory. So it was like it was run and the output exists, but it's within a container. So to get actually output within the host system, we can create in the host system output directory. And to our like previous command, you can add, because you can actually mount as many directories as you want. So you can use another -v output. And if you are lost, you can always go to page number 19, create the output, and copy paste this command. And you can run it. I make mistake because like -v has to be before the name of the image.
And also tell it to output to the output here.
What? Sorry?
The end there, sub-01_output.
Oh, yeah, thank you. Yes. So you also have to specify the output full path. Oh, typo, okay. I'm getting there, yeah. I cannot use type completion here. Okay, so now, Yeah, so does anyone need help? Or you have question about the command? So now if you check the content of your directory, you see that it's output because we created this directory, and we can go inside and check it. And you see that the output is in your host home directory.
Sorry, what does it mean when you have two -v's?
So -v is, it allows you to mount directory. So in this example, I was just mounting two directories. So the first -v is for like the data directory, and the second -v is for my output. Should I finish? Okay. So you have like more like 8 pages from my exercises. So you can see how to run, how to open an interactive session within Docker, and how to remove containers from your computer. So you can check this later. Okay, thank you.
Okay, so now we have pretty much completed all the overviews of the individual tools and building blocks that are necessary for actually conducting a reproducible or re-executable analysis as a first step. And what we're going to do now, or what we're going to start now, is actually conduct one of those analyses where we plug these pieces all together and produce something that will then be a candidate for archiving and re-execution exploration in the future. So I will just take a few minutes to outline that. So we will start from DICOM data that is available on the web for this demo. And by that, we'll simulate the situation that we just finished scanning, pretty much. And we got the data in a form that you would get it from an MRI scanner. And then we built, on top of that starting point, all the building blocks necessary. So we'll do conversion into nifty format in a bit structured data set, as you've seen in part 1. And we'll use a container with that DICOM converter to do that. And then we'll take a quick break and get yet another update on how to conduct analysis, and then we'll come back to this exercise and actually do the analysis with the container in a fully reproducible and re-executable way. So the concept or the implementation concept that we're using is also available in the DataLad software. So what you can see here is basically a depiction of a DataLad dataset. And you can see that at the lowest level, there are other data sets being referenced. So DataLad has a way that you can track other data sets, which may contain input data, in what we call a super data set. So what that does is basically tracks the version or the state of an entire database, if you want, right? So all your DICOM files that you acquired in a study could be in a data set, and an analysis data set could reference that. And then a DataLad data set can also track container images, like the ones you just created. And it can also track any kind of custom processing code that you usually develop or at least modify for a particular analysis. So all these things end up in a data set. And then the last bit DataLad will do for you is it will actually execute that custom code in the containers that you need to turn the inputs that you referenced into the outputs, and it will also track those outputs. So everything that is your analysis is then represented in one data set. And it combines all the features that Jarek mentioned before, so you don't have to actually carry the data around, so the stuff that you archive is really minimal. And with that kind of technology, we can conduct an analysis in a straightforward, pretty much if you've done it a few times, way that keeps all the individual components of an analysis separate but connected in the modular way. So you'll have a representation of the raw data as it came from the scanner, no bit changed, right? Then you turn that into an analyzable format like the bit structured data set. Then you can run one or more types of standard preprocessing or tailored preprocessing for your analysis. And then you conduct several analyses from that one, and they will lead to multiple publications, hopefully. And also those could be in data sets. So any part that you take here will be able to trace back to the very origin of any single data file that was involved in the production of a particular result or paper. And we'll do two steps here. First, we'll do this conversion or this step from going from the raw data into the bits structured data as a first. These are the commands that were up during the break, and I hope they all worked out for you. And if you now click not you don't click on this link, but this is the same page that you were on before. So I will now open this in the virtual box itself, if it lets me do that. Okay. Give it a second, and I put the page side by side. So the page you need to go to looks like this. So everybody up? Cool. So what I just said is written down in the introduction. So if you scroll through that page, it has tons of text. It's not meant that or it's not intended that you read through all of that. So I will guide you through this, but it should be comprehensive enough that you can go back next week after the conference and reproduce all these little things. And there's also the outcome of this analysis also on the web on GitHub for you. The link is at the very bottom if you make it through. So you can skip the entire introduction because it contains, with a few more words, simply just what I said right now. It's important for those who haven't done that yet to activate the software environment. But if you've executed any data-led command so far, you've already done that and you're safe. You can create a separate directory for this lesson if you like. So again, the introduction just has the narrative that I just gave to you. I'll give you a few more information on the way. And so here we have the section that this first exercise will be about, which is, as I said, the conversion of the raw data from the DICOM format into the bits format. And the DICOMs that we provide, you will see the URL in a second, they encode study metadata already using the repronym naming conventions, which allow you to put things like the label of the task that the subject performed during an acquisition into the protocol names of the image series. So you can sit at the scanner console when you plan the acquisition and put all that information in. What we'll do now is we'll use a tool called UDiConf that can use that information and generate you a bits compatible or bits compliant data set automatically, so you don't have to actually edit files as much. And anything that we do starts with the creation of a data-led data set. So unlike the consumption of a data-led data set that you already did by downloading the 114, we'll now create one. So the first section is about creating a data set called localizer scans, because this is the type of data that we're using. It's a fusiform phase area localizer experiment. So use the create command to create such a data set. And put your pink sticker up if there are any unexpected problems with that. And if you can do that, you're perfectly set up for the rest. You what? I was audible. So again, this is the page, reproducible imaging org that you've seen before. OHBM training. I think I've seen this on everybody's laptops. Anybody did not find that page? Okay, all good. So we don't fix a problem that doesn't exist. Okay. So it's kind of straightforward how to do this, and we'll do it. We'll do it right here. I'll create. Is that big enough for you, like this? Yes, sure. So we'll create a folder, lesson 3, and enter that folder. So everything is. Yeah. So and now we can. See, I activated the environment. It tells me in the prompt. So I have data led. I can do data led, and it tells me, yes, I work. And then we do data led, create localizer scans. And it creates a data set, does something, and tells me it's okay. Whenever it tells you okay, it thinks it's okay. So we go into this folder, make it a little bigger, and you can see that there is pretty much no content in there other than a few hidden files. So what you created is simply a Git repository with a few additions that are data-led specific that we don't have to worry about for now. And now we will create this link between the raw data that's provided on the web and this data set, which will contain the converted data structure that is bits compliant. And we use the install command that you've already seen with one little twist. There is one option that you can give to register another repository which lives on the web. Here, the link to it is behind this word GitHub here. So if you right-click and say copy link location, that's the link of the dataset that we want to install. So now I'll already type it in, so we can use the install command, and then we specify the current folder as the dataset that we want to install into. And you can see in the prompt I'm in the dataset localizer scans. So the dot is a shell symbol to reference the directory that I'm currently in. And then I'm telling it via the source argument what do I want to install. So I can just give the URL. This is the link you can copy, and then I tell it where in that data set should this new data set be referenced, or it's actually not a new one, but the copy of this data set. And we go for inputs raw data. There's not really a convention, but it's nice to have all the inputs in inputs or some other folder that you want to have. So we can execute that, and it will obtain about 20 megabytes from GitHub. So it might take a second. I'm doing it live. If it takes more than a few seconds, I'll show you the results, and we'll have it run in the background. I guess I'll show you the result right away.
Who is familiar with Git submodules or ever used it?
Oh, it's done. Awesome.
So that's the mechanism which is used here to link one data set within another data set.
So we see that it says it installed okay, and it reports us some actions that it performed. It added something and saved something. But what we're really interested in, we're interested in the sub-dataset list. And sub-datasets. And it will tell us that it created a it established a sub-dataset in this folder. So we now could take a look there, say inputs, raw data, and it has a folder structure that it obtained with tons of DICOMs. So we now have established that reference between input data within the data set that will contain our output data. And now we've learned that, software environments are volatile things, and we really want to keep track. And DICOM converters are particularly interesting to keep track of because they're pretty much the first thing you do to the data. So if they have any problem, everything will have a problem, right? So you want to insulate yourself against sudden changes in the environment, and we can do that by using a container. And the way to do this is Datalite has an extension which is installed for you. It's called Datalite Container that gives you 3 management commands: one to add containers and one to run software within containers. Pretty much like the Docker run that you just saw, but with knowledge of what a dataset or Datalite dataset is and where it stores its images. So what we can do now is we can Datalite containers add a container, and because we don't want to spend all the time downloading things, we're doing something that is actually more complicated than what you would do at home. So Datalite containers add takes a name of a container. Here we're using the name of the software that's the prominent guest in that container. It's called HeuDiConv, Heuristic DICOM Conversion. It's one of the possible DICOM converters. This one is interesting because it automatically can generate a bits compliant data structure. And then we could just simply give it the URL to something that's called Singularity Hub, which is the same thing as the Docker Hub, this exchange platform for images, just for Singularity. But we are going to actually use a local copy of it, which lives in your images HeuDiConv simage file. And then the call becomes a little more complicated because it doesn't know that this is a Singularity image, and we have to tell it how to execute that thing. So you've seen Docker run before. With Singularity, you can say Singularity exec, and then the name of the image as you've done it just now, and then the command, which is what we're providing here. And then we can say Datalite containers list, and you need to type it correctly. And it tells you, okay, I have a container in this folder, and it's an image file. That's how Datalite represents that container inside. But the thing is, now that it's an image file, and it knows where to get it. So in our case, it knows that it comes from this folder in the VM, but if you would have used this command, it will actually would have resolved the URL to that Singularity Hub image file, where it actually lives somewhere in the cloud, and reference that within the data set. So you can reobtain that later on, even if the Singularity Hub front end is no longer there. And now you also have a copy, and the system knows that you have a copy, and you could share that copy, and it will keep track of that copy that you have outside of the reach of Singularity. So now we have all the bits pretty much in place. We have referenced the input DICOM data. We have a computational environment that contains the software that we want to run. The only thing that's left to do is we need to run it. And Datalite will take care of the entire rest. So it will run the software, it will see what data artifacts, files, directories it produces, and it will capture all the outputs and reference them. So unfortunately, HeuDiConv is a very capable beast of a software and has many, many options. So I'm not even going to make the attempt to type this in, but I will illustrate what it does. So I'll put in the pieces that are important. So we call Datalite containers run, which is like Docker run, the thing that runs the container. And then we can tell Datalite to record the change produced by this command under a specific message. So there's -m or --message. So what we do is we convert subject to's DICOMs into the bits format. This will then be the human readable message in the history of that data set. So we know this was our intent when we ran that command, right? And for some people, English is better readable than shell commands. For some, shell commands are. Definitely the shell commands are the more precise language. And then we don't actually have to do it, but for the sake of demonstration, we do it. We tell it what container to run this command in, which we'll follow now. If there's only one container, data will figure out if you're running containers run and there's a container, we'll run this in the container that we know, right? But you can also have multiple containers and switch between the two. And then this thing has nothing to do with data-led. This is the UDICONF command that actually converts the DICOMs, and the essential bit is pretty much this one. We pointed to the folder that has the DICOMs. And now we can run this thing, and it will produce awesome output, loads, that you can study next week, what it's trying to tell us. So it's reading in 5,000 DICOM images while I'm trying to bridge the gap. And then it will analyze them. It will look through the metadata, which is in the repronym conventions, and then it will sort out what will be the bits compliant output file names for each DICOM image series that's in the data, and it will create a folder structure that is in the right format, and it will add the JSON metadata files that you created by hand in the beginning automatically, and then DataLad will capture that result. Yes? We need a microphone there. Yes. It's a little more than a wrapper, but this call, and I think so this part here tells it for the actual core conversion, it uses DCM to NIX. But all there's stuff around it, like the sorting of the DICOMs, etc. That's done. You could achieve a similar result with DCM to NIX yourself. You lose a little bit of the convenience. And DCM to NIX wouldn't be able to interpret those repronym conventions. And the link to those is in the documentation.
Question here.
Yes.
What is -o/tmp UDICONF? Why is it there, and why not inside the data set?
Yeah, I'm in a conversation with the UDICONF authors to make this not necessary. Right now, it helps us go through this exercise. So almost done. So now the actual conversion part is finished, and the metadata files are being created. And then we'll see in a second what files it has produced. And we have 3 minutes till the coffee break, and we'll make it. Here we go. So you can see that DataLad tells us what files it has added to the repository. I'll make it bigger for a second. And you can see that it figured out file names that looked like they're bits compliant, and they actually are. And now this whole thing is encoded in the dataset's history. So there's a tool called you could use git log to figure this out. And there's also a tool that's called TIG that I like to use. It's Git spelled backwards, which gives you a little bit better representation. So this is the change we recorded in the data set. See that DataLad recorded what commands we ran. It also captured the files. And all these files are now in this Git annex thing that Jarek mentioned before. So their identity is tracked, not the content. The content is local, as you would have done that before. but you can now move the content also elsewhere, which is something that we're not going to talk about. So the only thing missing now that we have to do in order to be able to actually analyze the data is something that we cannot get from the DICOMs, which is the information, what kind of stimulation that subject received at what point during the experiment. That usually comes from a text file that is generated by your stimulation implementation. And in bits, there's also a standard representation for this kind of information, which is called the events TSV files. You have seen TSV files before. And the data set that we got from GitHub already has the right file in the TSV format. It just doesn't have it in the right location. So this exercise tells you where it will live. And after you've digested the section 1 of today's exercise, that shouldn't come as a surprise to you. What might not be yet very obvious is that we need to capture this I got this file from somewhere step also in order to make this entire analysis completely reproducible from the raw data. Because any file that you just copy in here and you git add to the repository will have no information of where it was coming from. But in this case, that comes from a data set that we got from the web, and we need to capture that information. And if we can even use a data-led command to capture the output of a simple shell command like copy that you've used before, and so we can simply do this. I'll copy it in here for speed reasons. So we can call data-led run, which is just like containers run, takes the exact same options except for it doesn't work with containers, it works directly in the environment because copy is a built-in command. And we tell it what we're doing. We're importing the stimulation events. And now I'm going to show you a feature that it has. So we can tell run what are the inputs into a command and what kind of outputs are we expecting. And if we do that, even that kind of information is captured in the record that data will be produced. So you can ask that data set, what are the inputs? And essentially what you're building up is a graph of information, what inputs across many, many stages of processing were responsible for producing an output. And now you're saying, oh, but now I have to type everything twice because it also needs into the copy command. But that's not true, because in data-led run, you can use placeholders to reference everything that you specified before. So we can now just run this, and it will do nothing but copy the file from the location in the subdata set into the location that is relevant for the bit standard, and we'll have that step covered. So if we look at the history again, we can see it captured the record and already produced a reference of the result, and it stored it under this hash in the annex. So what you now have, you could take this data set to the bits validator, and it will complain about a few things that it couldn't guess. For example, the version it's compliant with, the name of the data set, etc. So anything it doesn't, it cannot extract from the metadata that it has access to, you would still need to fill in manually. But the most important bits, like here's the participants TSV file, these things are pre-populated automatically for you. So it's a really cool thing because you think less and rely on the expertise of all the other people that contributed to this piece of software. And this is where we'll pause for the moment and go to the coffee break, and then we'll take this data set and turn it into an analysis. Yes, we need a microphone. Where do I find what information? In here? That is because the age and the gender of the subject is coming from the DICOM metadata. So you encode that prior to the acquisition stage. You register the patient, and then you have to type in the weight for the SAR limits, etc., including the age and the gender.
And how about the fact that it's a control subject?
I think this is DICOM making a bold statement that it's probably a control subject. But you can, so these files are editable. You can just go and correct that, and also add all the other variables that are interesting in your particular context, which may or may not come from or maybe in the DICOM metadata. So questionnaire items, that kind of stuff can all go in there. Coffee or questions? Coffee.
So let's have a 15 minutes break. I think that's, yeah, 1:05. Come back before 1:05 minutes.
Yeah, I deleted that, but the
think they had like warnings that it was only warnings, but that they cannot find entry point.
Then they haven't.
I mean, it's working. It's like I
No,
don't know why.
no. But then they have not done this part.
Maybe they
Because
said that they did.
Hold on, so can you point me to anyone?
Oh, she's gone right now, so I can show you. I mean, I can show you her computer. I guess.
So if you ran any commands in the previous section and you got warnings of the style entry point, something, 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 broken, error, then can you go back quickly to the...
Oops.
Okay. Oh, now for you.
I'm closing tabs by clicking on them.
Then you rerun this line, and the important bit is the full in the brackets. It will pull down a few more packages, takes a few seconds, but then that whole warning thing goes away. There's the left button, right button.
And this, close.
Left button, right button.
All right, I think I'm going to get started. I think most people are back. Can people hear me well? All right. Before I start, so I'm going to click on Neuroimaging Workflows over there if you want to follow along some of the pieces. I'm doing this a little bit of a tag team with Michael. We're trying to figure out how to get the most of these workflow processing things and data lad into your fingertips and finger memory. But before I start, I just want to say a sentence or two about ReproIn. So you downloaded a set of DICOMs and you were told that it was formatted or collected using the ReproIn standard. And what the ReproIn standard really is about taking DICOMs, or when you're at the scanner console, naming them in a particular way such that DICOM, the tool that you use to convert it, can do an automatic conversion of those DICOMs to bits. So manual conversion of DICOMs to bits takes a fair bit of effort. You need to organize things in a particular way. By naming things right at the source, you simplify the conversion process. Now, if you don't have the capability of naming things at the source, and that's true of some scanner centers, then you can learn about additional characteristics of DICOM, which allow you to create what's called a heuristic file, hence the name heuristic DICOM converter. That's where DICOM comes from. That you can take either existing DICOMs that are not in that format and convert it to bits automatically through this heuristic, or current DICOMs that are not labeled that way. So just wanted to make that out there, and if you have any questions, talk to Jarecka about ReproIn naming. Okay, so this part has a presentation which I'll be giving, and I'm going to try and keep that short. I'm going to try and tie up some of the things that have been discussed over the morning and till now. And then there are two exercises. Michael is going to do the first exercise. The second exercise, for sake of time, is listed there, and you should be able to deal with it later on. If we have time, we can come back to it, but I think just given our schedule, we're going to skip the second exercise for now. But it's all there, and you should be able to follow along with it later on. Okay. So I think you have been executing some computation, and most of you have done some bit of processing in your life for your various research projects. We're going to talk a little bit about what executing computation really means, but more importantly, from a reproducibility perspective, what does tracking computation mean? And then there'll be the exercises to work with this. We tend to abstract things out. We write scripts, we click on GUIs, but there are many sorts of things that allow various kinds of abstraction. And really, the reason we go and do this abstraction is so that we can do certain things like reuse components, that we don't have to write scripts for every single data set we collect. And there are many ways to process data. Many of us are familiar with various kinds of GUIs. We use different kinds of shell scripts, Python scripts, R, MATLAB scripts. All of these create procedural abstractions. And so if you're sitting on that command line or inside a MATLAB or an R shell or terminal and typing things every single time, you abstract away what you want to do with the data away from the data itself. But there are also data flow frameworks, and one of the frameworks we work with is NiPipe, which is a Python-based framework for neuroimaging, but there are MATLAB-based frameworks like automated analysis and PSOM as well. So depending on your flavor of tools that you want to work with, there are many things out there that may help you abstract away the computation you want to do with the data from the data itself. And then if you structure data in, say, BIDs, you also get an abstraction that allows different kinds of applications to run automatically on a BIDS data set. So whether your data set A is a BIDS data set or your data set B is a BIDS data set, you don't think about it very much. You can run the same kinds of tools. And then you learned a little bit about containers, and that was really a very surface-oriented intro to containers. They have a lot of powerful capabilities. I would highly recommend you to look at Docker and Singularity, depending on the kind of environment and setup you have. Now, most of your local laptops would be able to run Docker without any problem. For Windows folks, you may have to do a little bit of tweaking to get things to run, but in general, you should be able to install some version of Docker on your local things. For Singularity, you would have to get to an HPC system unless you're using a Linux laptop, in which case you can run Singularity on a Linux laptop quite easily. So we think we do this because of certain principles. First, as we were talking about, separating computation from data flow or data management. And that's really the first abstraction that we do when we write scripts or create workflows, is separate these two things out. We also like to be modular. Instead of a one giant script that does everything, we try to say, can we create reusable pieces? And if we create reusable pieces, we can share those reusable pieces. As you already have used certain things, there's an FSL container there, there's a HudiConf container there. Yes, they're simple enough containers that you could recreate any single time, but you can also hand them off to somebody else and they would have your exact environment. And the same thing can be said of code or scripts that you write. And if you put them out on GitHub or some other venue, then other people can reuse things. We do a lot of things that are similar across different projects. And the more we can reuse over recreating, it actually helps catch a lot of bugs that happen in workflows. Standardizing inputs and outputs. You got a bit of a flavor of NIDM, and you've mostly heard about BIDs. But these kinds of abstractions allows us to create things where our tools and our scripts can make assumptions. This is how I expect to find data. And those assumptions, if you can standardize those assumptions, that makes it easier to write scripts and tools. So using standards are very useful in making sure that you can reuse things that you create. Being interoperable. If you think of all the packages that are out there, there's certain packages that can't do certain things, and there's certain packages that have certain advantages over other packages. So you may want to switch around or move around from package to package for different aspects of processing. And if you can write scripts, if you can encapsulate them, if you can use environments such as containers to install those packages and reuse them, now you can start using these different packages quite easily. Dorota mentioned NeuroDocker. It can install SPM. So for those of you who want to use something from SPM alongside something from FSL, you can do that within that container framework. So it's quite nice to have that kind of flexibility around such that you can optimize the kind of processing you do instead of thinking about, oh no, how do I switch to X? And probably the most important thing is this idea of encapsulation and isolation. We start working on our laptops, and not just our desktop gets cluttered, everything gets cluttered, because we start installing everything into our home directories, into our systems. And we really don't know what interactions are happening across software effectively within those cases. So by encapsulating things in these isolated environments, we allow for very precise control over the environments, even if our desktops are cluttered with all these isolated environments. And that's something I think worth thinking about. I used to say when I first started grad school, my workflow looked like the one on the left. More recently, this is almost about 20 years later, it looks like the one on the right. And things have gotten complex for various reasons. Complexity might come with workflows being more robust, things that are able to handle different kinds of things. Complexity might come from new tools that can deal with certain pieces of data better than others. But nonetheless, complexity can increase in various ways. And keeping track of this through just writing scripts or rewriting scripts can often be difficult. And I think using data flow frameworks allows you to abstract away such computation from your data sets quite nicely. Well, scripts do not work by themselves. So you need to install software. And this is just an example of software supported within the NiPi platform. We use a lot of different things for different kinds of things. Let's say you were doing diffusion SPM for functional MRI analysis. SPM doesn't have anything for diffusion analysis. You might use FSL for diffusion analysis, but then you may want to integrate the results of things. So these kinds of data flow frameworks allow you to integrate and interoperate across these tools. Now, it does place a cognitive load. You need to understand how these packages operate. And that's like learning anything in science. If you're doing neuroscience, you're learning about different parts of the brain, different cognitive processes. Doing software or using software, you should go and learn about the different pieces of software that are out there. There was a mention of virtual machines. You've been using it all day, and that's an encapsulated environment within which we've put these tools that you can use. But you can also go and do things in the cloud. Amazon, Google, Microsoft all have cloud services, which are these encapsulated environments within which you can process things. And there are many tools out there that allow you, Nitrix-CE being one of them, that create these containers in the cloud that you can process things with directly online. And NeuroDocker is something that you can use locally. So it's a little bit of a misnomer today because it started off creating Docker files, as you saw in the example, but it can also create singularity files. So it really supports both kinds of the dominant container abstractions that currently exist today. And then the question is, how do we track all of these things? Well, this is where the term provenance kind of comes in. And we don't think about provenance directly unless you're an art dealer or somebody who deals with selling art to different places. But the same kind of thing applies to all the things that we're doing. Michael showed a very nice example of how data lab can be used to track what inputs and outputs are generated by a process. And if we think about that step, well, those inputs and outputs are entities. That process that we executed is an activity. And since you all executed that process within your virtual systems, you are all agents helping with executing that process. So the simple frame of reference of thinking about provenance allows you to encapsulate the different pieces. And down the road, different people may look at different components of this provenance. So why should we track information? And this is kind of asking the kinds of things that you may think about doing later on. You may have seen a paper and you want to repeat the analysis. It's really hard to do, but if you tracked your provenance and submitted it with the paper, it's likely that somebody else would be able to repeat that analysis. You might want to reuse analysis on similar data. This is the abstraction component. You can apply the same process to a different data set. Visualize analysis steps. I already showed you 2 different workflows, and I could visualize the different components of it. Find software that was used. We've talked about the complexity of workflows. We are looking at different versions of software that are being used, and tracking provenance allows you to track those different kinds of things. You can query the parameters, you can review and verify the intent, you can reuse part of the analysis, discover related analysis. There's a whole host of things why tracking provenance is important. We tend not to do it because it's complicated. But as you just saw, even using something as simple as data lab to annotate or record, it's like a recorder really. And you're recording those things step by step as it goes along. We can then look back into the logs of those things and retrieve all this information in some structured manner. So what should we track? I'm going to throw that out as a question. You've done a lot of things today. The history. Okay. What in the history? What has changed? So something about the data, perhaps. What else? The scripts as well. So the kind of scripts that you were running. What else? The location where data are located. So properties of data in some sense. Okay, so I'll put that under the data umbrella a little bit, yeah, but software used. And what do you think about software used? What in your head is a software? Packages and their versions. What other aspects? If you're using a GUI, there are options. Hopefully that GUI allows you to record how you're clicking on the GUI. Otherwise, it becomes very difficult to repeat some of those things. And that's one of the biggest challenges with GUIs, and the reason why people don't want to rerun things, do things, and why scripting or doing scripting things is quite useful. Anything else? Well, there are a few things. So actions, I think, covers the GUI clicking bits a little bit. Hopefully they're tracked. The environment really comprises not just of the top-level software, everything down to the operating system. And we don't always think about that entire stack when we are dealing with this. So how do we track these things? Bash history, you learned about that today. Even at its basic level, that's recording what you did. So that's a good place to start, even if you're not doing anything. Script is another Unix command, which kind of turns on a recording diary. But I would encourage you to move from 1 to either 2 or 3 or both somewhat. So you'll be hearing a lot more about DataLad as you go through the next exercise. I just want to touch on ReproZip a little bit. So ReproZip is a tool not very much unlike DataLad in the sense that it captures information, but it actually captures only the pieces of information that were used to process something. So if you think of a package, how many people here are familiar with FSL as a software? Or, okay, most of you. And those of you who don't know FSL likely have used SPM or FreeSurfer or some other tool. And these packages that come out have a lot of software or binaries inside them. So you can not only do BET for brain extraction, you can do GLM analysis or other things. But for any execution step that you use, you're not using all of that software. You're using pieces of it. And as you saw when Jarecka was talking about paths and how easy it is to perhaps switch the order of where a particular binary is coming from, it's important to know what exactly was used. And ReproZip is a tool which allows you to capture that piece of information. Exercise 2 deals with using ReproZip. We're not going to do it right now, but since it's all in this document and it's available on your virtual machine, you can deal with it, work with it later on. So at this point, I'm going to stop and I'm going to let Michael take over again and do some GLM analysis.
So, me again, and we're back exactly where we left off. And as Satra said, we're going to do a GLM analysis. So, to bring you back to the state where we were, we created a data set that contains the imaging data that was given to us in DICOM format, and we generated a bit combined data structure. Now this, as I mentioned it before, if you want to conduct a data analysis in a modular way, then this is a useful input to a variety of possible analysis that you could run. You can also incrementally build on it by acquiring more scans from different subjects or from the same subject, etc. And what we'll do now is we'll try to put all the pieces together that Satra mentioned and build an actual data analysis that will really run and gives you something that captures this entire provenance information at some level, and encodes it at first in the structure of a data-led data set, which then could be inspected in order to produce a more formal representation of aspects of provenance in the format that Sandra mentioned. So the key bit here, we'll just return to the directory that I made. So last time we created this localizer scans dataset. And the first key thing to remember is that we want to produce a modular analysis. So what we'll do is we'll create another dataset for this step. Now, the purpose of this dataset is now to capture all the inputs into the analysis, all the computational environments necessary for the analysis, and any custom code that we need for the analysis, and then it will finally capture the outputs of the analysis. So we'll do the same thing that we did before. By the way, everything here conceptually is just a replication of what we did in the previous exercise. So create dataset, add a container, run something. Just that the steps are now different because we're doing the very commands are different because we're doing a GLM analysis using FSL, which seems that most people are familiar with. Did the conversion work for you before? Yes. For whom didn't it work? Awesome. Would be bad, right, if it's reproducible, supposed to be, and doesn't run. So we create a new data set, which you can name any which way you like. I went for GLM analysis. And of course, it could be more specific if it's targeting a specific kind of analysis. So same command as before, and we end up with a second folder that is not inside the localizer scans that we used before. So we enter that folder again, and now you can probably already imagine what we have to do, because now the inputs are no longer raw data DICOMs, but our bits data structure that we created before. So we have to now use the install command again to register that data set that we produced ourselves as an input for this analysis. And it's exactly the same command that we ran before. Put this up here. Just that the locations changed. So install, we want to add this to the data set that we're in. Remember, the dot is symbol for referencing the current directory. But this time, our source is not someplace on the web, on some server or workstation or anything. It's just one directory up the data set, which we call localizer scans. So we can also reference local resources without any issues. And we'll follow the same convention that we used before and put this input data in a folder called inputs, and we call it raw data again because it's still the same raw data, just in a different format. But of course you can decide to use other names. So what it did now is it made a copy. And there are many options that we are not going through right now for time reasons, but you can make that copy real cheap. So for those of you who know what hard links is, you can instruct this command to hard link things so it won't use duplicate storage space. It's really fast. But the point is that now on your file system, you made sure that you do not modify the original bits data file. So there's no accidental modification by you changing files randomly, trying things around. So you have your original data set in a nice and secure location. And we have an independent copy now in data-led sub-datasets as a sub-dataset in inputs raw data. And now the following command is the most obscure in the entire thing because we'll do the Jedi mind trick and run the following command. Data-led run procedure set up Yoda dataset. That's not a joke. It should actually run. It ran. What this thing does, it sets up a particular configuration for that data set so that we track custom code, which we'll do in a second, in Git as it would track any other data set, but track large files in a Git annex thing. And it applies a set of conventions that if you like them, this thing will automatically take care of for you. If you want to learn more about that, you can come to the poster 2046. It's not the number that is on the paper that I have in front of you, which will on that poster you have lots of information of how this organization structure is meant to be, and we think it's quite useful. So now, for those of you who've done an FSL analysis, you know that we need a bunch of files in order to do that. So standard GLM analysis, you need information about when the simulation happens, but FSL doesn't understand bits, events, TSV files, so we have to bring them into this information, we have to bring it into a form that FSL can understand. We're going to use so-called EV3 files. For those of you who don't know FSL, these are basically text files that tell you when the simulation started, with what intensity, and how long it lasted. And the other thing that we need to do for an FSL analysis, we need to fill up a text file with all kinds of variables that instruct FSL exactly what kind of analysis you want to run. If you're an FSL user, typically what you do is you use the FSL GUI to basically click together an analysis and then save a file, use that as a template, and replace certain variables in them, change the ID of a subject and the number of a run, and then you can generate from that one file that you created by hand all the other configurations for all the other scans of subjects that you did in your study. And we'll do a similar thing, but we're trying to make it re-executable, so we have to cut out all the manual steps so the machine can do everything, because it's hard to capture the click on the button. So first thing we do is we add the necessary information to that data set that we just created in order to capture all the inputs. Datalet has a command called download URL, which I will copy paste. So the interesting bit is download URL, that's the command, and we want to download all the content from the list of URLs that we're giving at the end into a folder called code. And if you look at those URLs, what you can see is we're basically downloading scripts that are provided in some repository on GitHub. So I'll just copy that in, and we'll see what happens. It will obtain those files from the URLs. You can see downloading from this and that into code. And now we have a code folder that contains our scripts. And because we set it up using this Yoda procedure, we can actually inspect the history, and we'll see that the content of these files ends up being tracked in Git, like in any situation where people would use Git as a version control system for software development. So now we have two scripts in code. Let's look at code. We have this template file with the FSL configuration that I managed, that you would have created manually in some sense. And we have a script that can convert the events TSV files from bits into the format that FSL expects. And now we run that converter to create the input files for FSL, and we can use the datalet run command again. And we're using run again. We could just run the code in that script, but if we would do that, we would generate files that in the history of that data set would look like they would come out of thin air. We could have typed them in by hand, which is not the case. We're generating them from inputs, and if we want to have the full provenance capture of the entire analysis, we want to make a record that we executed that code. So executing that code would basically look like bash, name of the script. This script is written so you have to give the ID of the subject that you're generating these things for, and then you would list the inputs. And the corresponding datalet command looks pretty much like it, but as before, we're giving it an information what is input and what is output of those commands, because there's no maybe Satrajit will talk about it later. It's quite an expensive step to figure out automatically what a command needs as input and as output, and we're basically doing a shortcut here and just giving it explicitly. So we'll run that. It will take no time, and you will see that from that events TSV file that we copied in the last section, we created those input files, and they look very simple. We'll look at one, and those who've seen FSL EV3 files, they will say, yeah, this looks like an EV3 file. So first column is onset, second column is duration, both in seconds, and the third column is an intensity value that the FSL supports. And now we have all the inputs. The only thing that we need still is FSL. And it has been talked about at length before how important it is to know exactly what version you're using. And it's not just version of FSL that you're interested in. You're interested in every version of every software and library that FSL depends on, which is a long list. So we save ourselves from doing that by using a container. And there's a container for you at this Singularity hub URL. But as before, to save time on downloads, we're making a shortcut and using a copy of that container, which is already in the VM. So we did the same thing as before. We add a container image to the data set under the name FSL, which contains FSL. And as Dorota showed before, we could execute FSL commands like bet in that container without having to have FSL installed on the host system. And you can convince yourself that there is an FSL container by using the containers list command again. And now we are basically ready for analysis, and Datalet, like Git, has a way to tag stages in the history of a data set. So here we do Datalet save version tag, and we call this thing ready for analysis. So we can reference it under that name. So if you look into the history, you can see that it puts these tags as labels onto particular stages. So you can give meaningful names that are better than just dates in the data set. And now that's it. So we've repeated the step that we did before. We created an empty data set. We referenced all the inputs that are required for an analysis. We referenced a computational environment that has the software tools that we need to use. And now we're tailoring that template script for FSL for one subject. So who knows what the SED editor is? Not many. So if I can show you that template script. This, can I make this bigger? No, this I cannot make bigger, but it's not necessary. So you can see it has lots of files that are automatically generated by FSL. The only thing that I did is I labeled the paths that are needed. FSL needs absolute paths in there for any particular subject with those placeholders. And now the set command is an editor that can modify text files without me having to actually type something in. So this monster of a command here does nothing else but going through those placeholders and replacing them with the folder that we're in and the name of the subject that we want to convert. And we put all that through the datalet run command, and we'll inspect what the output will be, and datalet will tell us what it did. We get this thing, which is the tailored template file for this command. So now this has the actual folder name and the subjects. So now this is the complete setup, and now we just have to execute this. In FSL, there's a tool called feed, and the only thing you have to give it as an argument is the setup script, basically, that has all the variables with all the choices that you have in a GLM analysis, what kind of preprocessing, etc., encoded in it. So it's the complete description of that analysis. And what we'll do is we'll use datalet containers run with the FSL container to run this thing, and we give it a slightly more elaborate description of what are the inputs and the outputs in order to capture this information. By the way, this inputs and outputs thing is not required for data run or containers run. It's just there to give a comprehensive description of what this command does. And it will help you achieve the ability to automatically re-execute these things, which we'll see at the very end. So we run this now. And on my computer, this takes about 4 to 5 minutes. So in yours, it might be faster or slower, depending on, when you bought your laptop. So do you want to do the reproducible? Do we have time still? Otherwise, I'll just preempt the result and we look at what would happen at the end. Yeah? Okay? Okay. So I prepared the output or the outcome of this. So just to mention it, right? So what you see here after this line, this is FSL talking. And it will tell us we could go to that place and inspect the results. But the command is still running. And for the time being, we will look if I can manage. I'll take another terminal and go to a place where I have the results already prepared. By the way, I got those from a repository that is linked from the key points section here. So there's a link to it. And you can data install that thing, and it will give you the exact output of what you are all computing right now. And I data installed that before, so we can look at a few things. So for example, this is the GLM data analysis repository. So it still knows that there is inputs data, and it also has knowledge containers of the container that is there. Although source activate section 2. There we go. So it still has the container. This is where the container lives in the data set. So we can actually go into where we are in the data set, and we can ask git annex where it is. You've seen that before, and we can check whether it knows. And as promised, it knows that the image is actually available from Google's cloud storage system. So anybody who has installed that data set from GitHub has access to that image. They don't have to do the entire setup procedure, etc. And that will also work even if Singularity Hub goes away, as long as that storage unit is still there. And anybody who has installed it locally has a copy of that, and if you push that anywhere and tell Datalab about it, then there's permanent storage pretty much through crowdsourcing. So and now we can simply please let me look at the history. So this is the output, and we ran this command with feet. So this is the record of what we typed into the command line, and then it has captured all these things. This is the entire output file list that FSL produces, and it's not scrolling nicely for me. So there are a few more. So in the last bit I want to show you, which you can do at home to prove it, is the entire demonstration was done with the purpose of producing a recomputable analysis. But we haven't shown that yet, right? So for the complete picture, I need to introduce you to the so-called rerun command. So rerun is the thing that can inspect all these run records that Datalab created and re-execute them. So this command, which maybe just copy in here and make a little bigger. That's maybe too big. Lordy. You can tell it to re-execute everything since we made that version tag ready for analysis. So all the run records that were made afterwards, we want to re-execute them onto this tag and create a separate branch. A branch is a Git feature where you can have multiple versions of one data set next to each other, and we can re-execute that. And because we specified all the inputs and outputs, it is able to download all the necessary input files from their converted stages, etc., and put them in the right places for FSL to pick them up and re-execute the thing. So if you run that, you can follow these commands and use another command called git diff, which allows you to compare these two flavors, the original execution and the re-execution, and the outcome will show you that there have been no changes to any files, in particular to the ones that have the GLM statistics. The only changes between the branches will be files that contain timestamps and paths, because you re-executed the analysis at a different stage. So with this kind of setup, you get full modularity of any analysis that you can conduct, because you're limiting it to one step of the analysis per data set, so you can reuse those features, and you can also recompute. And you can get access to all the previous steps just from the latest data set that you might have published together with your publication. So in this case, if you go to this URL, you'll see what it is, and we can access all the sub data sets using the data get command that you've seen before. Now let's check where it is. So it finished for me, and you can see all the files that it produced. Now has produced a similar record as the one that we've published before. So one tiny last bit, we can also use the modularity of the analysis to save on archiving and backup costs. So du is a command that tells you how large the output of a command, how large the content of a folder is. So we have our inputs in inputs raw data. If you remember, that's the bit structured data set. But that's a separate data set. We don't need to archive the copy of this one because we use version control to know that it's unmodified. So we can tell DataLed to throw this away while actually checking whether there are any changes. So we can use the uninstall command like this to uninstall in this data set that we are in everything that is in the inputs folder recursively if there are multiple things in there. So we can do that, and it will actually check for all the files that are annexed with this git annex tool, whether there are enough redundant copies at other locations, regardless of where you got them from, and only throw them away when there are redundant copies. So it will prevent you from doing accidental deletions. And now we can check what the size of the data set is, and you see that we removed about 30 megabytes, which is about the size of the data that we had. So the information, though, about this sub-data set is still there. And it has the notion, and I'll show you that too for completion. And it knows precisely what revision of that data set it needs, also encoded as a checksum like Git does that. So now it can go back and reobtain that data set for you at that specific version. So if you need to recompute anything, DataLed is capable of doing that for you. So even if you haven't seen it, firsthand, I remind you that the text and the narrative in that lesson is complete enough so you can go through and recompute the entire thing. And if you see that you can recompute it yourself, go install the data set from DataLad and recompute that one, because it represents the state where you're basically replicating somebody else's recorded execution. So with this, you've seen all the tools to go through computational reproducibility or re-executability. I think this is a good way to end. Questions? All right.
So I know it's been a long day already. I think you guys need to shall we stretch a bit, get your arms up, ready to get the oxygen, because you will need the oxygen soon. We are starting the last bit of this course, and last but not the least, it's going to be a fairly different beast now. Please consider that what you've learned is absolutely is both cutting edge and both fundamental, right? It's both cutting edge because those tools are just being built. I think the version that you used of DataLad is, when was the last version that you released? 2 hours ago. So you've been using the version that have been released 2 hours ago of DataLad. So it really is a cutting edge sort of aspect, but it's also the principle of DataLad and the principle of how you handle the data and the container and those things are completely fundamental, and they are going to stay for a very, very long time. So consider that you've learned both the principles and also the cutting-edge technology to sort of implement those principles. Now we have, when we're talking about reproducible research, we are not only talking about being able to relaunch the same workflow on the same data. We're also thinking, okay, what if I don't have enough data? What kind of statistic I'm going to do, and is that statistic going to be reproducible as well? Like, is that going to give me like a strong answer to my question? So the computational aspect is fundamental. The statistical aspect is fundamental. So we are going to have a little quick preview of that statistical aspect with so Celia Greenwood is a professor in statistics at McGill. And she's going to tell you a bit on the p-value and power and refresh your memory on those things. And the reason why we think it's important to refresh your memory on those things is that despite being classical tools, I personally believe, and I think that's shown again and again, that these things are still not well understood. They are still, sometimes not clear what are those things and why they are so fundamental and so on. So I think a little bit of motivation. I think a lot of the irreproducibility aspect of science is coming from this reporting of p-value and how do we handle those p-values and how do we compute those p-values with the p-hacking problems and so on. So I think having a bit of refreshment on that part is really critical. And then I'll talk a bit on the positive predictive value, and maybe some of you know and some of you don't, but I'll do a quick summary of that, and then maybe if we have time, we'll do a bit more. But,
Thanks, JB. So I know it's the end of the day, and I know that you're probably getting really tired. So this will be, as JB said, fairly different. Just to start, what I'm going to talk about here in terms of scripts and whatnot, you can find on the GitHub page under section 4.1. due to a variety of technical challenges, this is not going to happen in the virtual box. I think I'm having hardware problems on my own computer, compounded with a variety of other things. So these are basic slides, which you will also find on the sorry about this, on the GitHub page. So I know you guys are all pretty sophisticated in statistics, and so that's great. And I'm going to revisit concepts that you should know, and just talk a little bit more about them. And at the very beginning of the day, it was said, we want to make sure that if you start with the same data and do the same analysis, that you get the same result, right? And so most of the day has been about that. Start with the same data, do the same analysis. How do we document that? How do we make sure that it is exactly the same? But what statistics is of course, talking about what happens if you do a different data set. If you're analyzing, we say in statistics, if you take the same data and analyze it with several methods and you get the same result, that inspires confidence. And that is always true. But going a little bit beyond that, what happens if you have more than one data set? And when do you make conclusions that are saying, you know, am I seeing something here that is consistent conceptually? It's not going to be exactly the same if it's a different data set, of course. But what conclusions can I draw from a data set? So that's where the statistics comes in, right? So this is the same idea about reproducibility, but it's reproducibly in a more general framework. So you guys all know what a p-value is. The probability of observing a statistic equal to the one seen in the data, or one that is more extreme when the null hypothesis is true. So let's dissect that a little bit. So I've highlighted a few things here. So observing a statistic equal to the one seen in the data. So that is bringing in right away the concept of repeating a study and repeating it in the same way. So the same study design, the same sampling scheme. So this is really crucial, right? If you want to analyze a data set that was collected in Montreal, where I live, and then you collect another data set in a totally different country in a totally different environment, and you're expecting to see the same result, that's a tall order. There's a lot of things that could be different, not just the fact that the study participants are coming from a different place, but also the whole way that the study design was conducted. So when you're talking about repeating a study, you really have to think hard about whether or not what you're going to get out of that is going to be reproducible. What has changed in the study design? What has changed in the sampling scheme? What has changed in the original data that is underlying? Now I've highlighted in blue the statistic. So if you're going to talk about reproducibility, you have to have a statistic. I mean, sometimes we forget about this. If you're doing a t-test, the t-test is the statistic, and that's, you know, that's fine. But that's not always what we talk about when we talk about a statistic. Sometimes the analysis that you're doing involves a very complicated workflow. And so your statistic is actually some kind of summary measure that involved a certain amount of filtering, or a certain amount of normalization, or a certain amount of data reduction or dimension reduction, a certain amount of, you know, deciding that I didn't like that observation. So when we talk about a statistic, all of that is built in. If you change any of those assumptions along the way, then you can't interpret your p-value anymore. And then, of course, the third element that I want to highlight here, and I've highlighted this in green, when the null hypothesis is true. So of course, you have to know what your null hypothesis is. And again, this seems very straightforward and something that you probably all understand very well. But if you have a very complicated workflow going on, sometimes it is a little bit difficult to figure out where your null hypothesis really should be. So again, I'm just going to highlight a couple of points here. So we know what p-values are. Let's say we have a statistic that has a nice normal distribution. And we know that the p-value is the area under the curve, and you've seen these in your basic stats courses. So if I have a statistic of 1, is this visible? It's not visible. Not visible, okay. But on the right-hand side in yellow, then I have a p-value of 0.159 for being the area under the tail. If I have a statistic of negative 1.96, that's your standard tail value that we often use for a 5% significance level, so the area under that curve is 0.025. Those ideas of area under the curve, they are not restricted to the fact that that was a normal distribution. I can define similar tail p-values for any distribution. So here I've done exactly the same thing for a gamma distributed statistic. So I don't need the normal distribution, right? I can define p-values for any distribution. And it's always true for any distribution that a p-value should have a uniform distribution under the null. And that's the definition of a p-value. For me, this is really quite a fundamental concept that sometimes gets lost, and this comes back to your choice of statistic and and really understanding what the null hypothesis is. Because when those things go wrong, then the null distribution is not going to be uniform anymore. The QQ plot is a tool that is extremely useful for figuring out whether you've got things right. So do your p-values really have the right distribution under the null? So if you have a whole series of test statistics coming from different data sets or coming from somewhere where you can get independence, then you can look at these QQ plots. This is just a plot of observed p-values on the y-axis, except I've done a log 10 transformation on them, against the uniform distribution on the x-axis, again, after a log 10 transformation. So when I do a QQ plot and it follows the diagonal line, then I know that the p-values I have follow the uniform distribution as I would expect. If I have some p-values that are popping out at the top, smaller, remember that the negative log 10 transformation here, smaller than I would expect, then those ones might be interesting. So this is a very nice tool to be used in this context. So the point I'm trying to make here is, we've talked about reproducibility in a technical sense. Reproducibility in the statistics sense is the idea of being able to make an inference. I see something in my data. I want to know whether the result I saw in that data is in any way transferable to the next set of data that I want to collect. So can I make inference? Can I go from the result I see today to the result that I see tomorrow? And this idea of making inference is tied to the p-value and tied to the testing process that happens. If you have deviations from that uniform distribution, then what's going on? Is it because I've made some, is it because there's something that's really exciting? Okay, that's obviously one possibility. But the other possibilities have to be kept in mind. Have I done something to the data along the way which means that the null distribution is no longer what I think it is? Do I really understand what the statistic is that I'm using? Do I really understand the sampling procedure and the population from which I've drawn the data? So that was all the null hypothesis. Now, of course, the flip side of that is whether there's something that follows the alternative hypothesis. Is there something real in the data? Is there some true association? So this comes into the idea of power. And as I'm sure you've seen before, we have two errors we often talk about with power. We have the sort of type 1 error, the probability of rejecting the null hypothesis when it's true. And then we have the type 2 error, or the beta, which is the probability of not rejecting the alternative hypothesis when it's false. And power depends on a few different factors. It depends on those two errors, depends on what you choose for alpha, what you choose for beta, and it also depends on the sort of separation between the distribution of your statistic under the null and the distribution of your statistic when the null is false. So here on the right would be, let's say, a distribution of the statistic under the alternative hypothesis. The red area is power, the blue area is type 1 error. And so you're going to have more power when the two curves are further apart. If I take a really simple example, which is just the t-test, you know the standard t-test for comparing two groups, you compare the two means, you divide by a standard deviation. When is the power going to vary? If the means are further apart, that means the numerator is bigger. It's also going to vary if the standard deviation is also going to depend on the standard deviation. Smaller standard deviations will make that statistic bigger. Larger sample sizes will make that statistic bigger. So power depends on all those things. Now, what I was going to do now is to ask you inside the virtual box to start RStudio and run some scripts. You can do that, of course. The R commands are located inside the set of scripts that are provided for you. RStudio and R are both installed. Technically speaking, given the time of day, I was actually thinking what I would do is just do it here, and you guys can try it on your own time if you so wish. So what we have here is a small data set, phenotypes.csv. And how many of you have actually run R before? Almost everybody, that's great. All I want to do here is talk a little bit about sampling variability. Basically, what I'm doing here is I'm reading in the data, creating some histograms of it, and then I'm going to sample from, this is just a couple of variables in the data set. The top left is a volume, a cortical volume. We have an age variable. We have a score, PHX. Jean-Baptiste, you remember what that is, JB? Okay. But I want to talk about sampling variability. So this is a data set that has 1,000 people in it. But what I'm going to do is create a small subsample that only has 30 people. And we can analyze this, and I can look at the size of the coefficients and the p-values. Here, for example, I have a coefficient of negative 0.9 and a p-value of 0.98. So I have almost no relationship there. Is that something that I would have expected to see, or is that something that I would not have expected to see? That's, if I sample only 30 people, I'm only going to get, I'm not going to have a very much power, right? Because the sample size is really small. And I also might have quite a bit of variability from one set of 30 people that are sampled to another set of 30 people that are sampled. And so what you have in this script here is code, if you ever want to try it, to sample 30 people, analyze it, and get a result. Sample 30 people, analyze it, and get a result. I've written it as a function. What I'm going to do is then just sort of go back to my PowerPoint and show you what happens. So here, there were 35 people registered for the course, so I did that 35 times. And there were two variables in the data set that I was focusing on. One of them was called gender. And there really is an association. It's just taking its time. It'll come up in a sec. There really is an association between this cortical volume and gender. And those are the red dots, okay? And these are p-values, and this is a QQ plot. Another variable in the data set was called mystery. The idea was to see if you could see an association, but let me give away the story. There is no association with mystery, and so those are the blue dots. So look at the p-values are ranging. This is on the negative log 10, so 3 is 0.001. The p-values are ranging from essentially p-values of 1 down to p-values of 0.001. And the blue dot range, they're not quite as large as in the red, but there's a lot of variability. I'm really spanning the spectrum here across these 30 points. I find this plot perhaps even more interesting. So again, the y-axis is the p-value with the negative log 10 transformation. And the x-axis is the actual slope coefficient. These are just simple linear models. So these are the slope coefficients. So look at the slope coefficients for the red dots, which are gender. There's a huge variability there, going from almost 0 all the way up to 500. It's the same data set. I have done random sampling of 30 people, and I've done it 35 times. So don't forget about the importance of sampling variability. Sampling variability is huge. It's just a really big difference from one data set to the other. And I haven't injected any bias. You know, when we actually go out and collect participants for study, there's bias involved there. There's no bias here. This is a nice random number generator doing the sampling. Even when there's nothing going on, when the blue dots, I'm getting a lot of variability from negative to positive. And you might say, well, sample size of 30, that's really small, right? What if I do it with a sample size of 100? So now I've got the QQ plot on the top. Okay, I've got more power. Sample size is 100 now. So all of those red p-values are small. They're all way above the diagonal line, which is this diagonal solid line. So I've got a lot more power. The p-values are smaller. But if I look down at this volcano plot, I'm still getting huge variability in the actual estimated coefficients of the strength of the association between gender and the cortical volume. If I go to 250, I'm still getting quite a lot of variability. If I analyzed all, there was 1,000 people in this data set. If I analyzed them all, I would have ended up with a coefficient about 115. Okay, so somewhere in the middle of the pack there. So you're still getting a lot of differences between estimates in sampling variability. So this is something I was asked to show, just a comment about a survey for the course, but this course is not done. JB is now going to come up and talk about positive predictive value. But some questions? Okay.
Remember that the group of 30 is basically the average group in fMRI, right? I mean, it's not a crazy number that we've seen in neuroimaging. Yeah, some people actually use like maybe 16 subjects, right? We've seen 16. So I apologize in advance because it is late in the day, and I think we're all jet lagged and tired. And I'm going to show you a couple of math figures. So that's going to be tough for me as well. All right. So let's see. Okay, so maybe the first thing I'd like you to do is to make sure that you have the latest version of the GitHub repo. And so if you go into your virtual machine and go into section, where am I? Into section 4. Oh, what's that? Workspace. In And if you just pull the latest version, well, I'm just going to make practice of what you've learned a bit before. So that's section 2. Okay, so our GitHub repo again. I think you have cloned it already in that machine, right? Is the GitHub repo name and then OHBM training. Okay, so if you clone or download that GitHub repo, get that in the virtual machine, and then maybe what we do is so I'm going to deactivate the section 2 conda environment, activate, and then source activate the conda environment that is the for section 4. How's it called again? Is it section 4? Section 4, right? All right. And then maybe going into the workspace and then git clone this GitHub repo. All right. Oh, so because that's a vagrant machine, I think we need. That's because you use the SSL and not the HTTP. Yeah, that's right. So let me get the HTTP directly from here. Thank you. So that's going to just to make sure that you have that GitHub repo, and within that GitHub repo there is a couple of Jupyter notebook, and with that environment you should be able to run those notebooks. So I'm going to just go to the first one. Yeah. Right. I don't think we have actually. Indeed, I'm sorry. Yeah, we usually. I mean, there's a number of people are very used to working with those documents. So Jupyter Notebook, and you have the environment to to create and to run those documents in your virtual machine. But a Jupyter Notebook is well. Let me show you. It's an interesting hybrid document that will mix text, possibly LaTeX formulas, as well as a piece of code. And in this specific example, I'm using Python code, but you could have a Jupyter Notebook with R code, or you could have Jupyter Notebook with Julia code, and there's about 20 languages that are, so if you want to install the Jupyter Notebook, just go onto the web, search for Jupyter notebooks, and you will be directed on how to install those things. But you have already the Jupyter Notebooks installed in the environment that we've provided with the virtual machine. So that's what the Jupyter Notebook looks like, and this is, and I can if I do Shift Enter, I'm just executing those cells. So it's a list of cells, and that cell. If I go into that cell, if I look at what is there, it's actually just a markdown file that says, okay, this is a 1 dash, and it says that this is a title. So, and if I execute that, I have the visualization of that title. So in the same way, if I look at, I was looking at making some definition here, making sure that we have on the same page of all those definitions, I can write some LaTeX formula here, and that will, if I execute that, the Jupyter Notebook will actually render those things as formulas. For the moment, I will just put those things a little bit too much in a little bit nicer place, nicer way. And the one thing I would like you to understand is what is the positive predictive value and why it is important to think of the positive predictive value when you're doing your experiment and when you're reading papers that have done experiment. So those are the reminders of the definition, and we have seen with Celia's talk, all those things already. So I'm going to call power W, which is 1 minus the type 2 error, the false 1 minus the false positive rate. And again, the same sort of notation, alpha is still the false positive rate as usual, and so on. And maybe the two new notation is that I'm going to call TS the test when it's significant, and Tn when it's not significant. So what is the positive predictive value? I don't know when it was introduced in the literature. Maybe Celia, you can help me with that. But definitely was introduced at least with the Ioannidis 2005 paper, and way before. When there was Selke and Berger and all those people. But when it came, I think it came a bit into fame for the general public. I meant. Is that there was this very famous paper saying why most of the results are false, and that paper was taking that positive predictive value and showing with that statistic what was the problem. So what it is the probability that your hypothesis on the alternative hypothesis. So the thing you are interested, let's say you want to show some association between let's say age and the hippocampal volume, for instance. Let's say that showing, telling that hypothesis, the probability that the hypothesis is true, knowing that you have a significant result for the test that you've done with on this association. So let's say I do a correlation, I find a nice 0.6 correlation, and that's maybe that's a p-value of 0.01. What is the probability that this alternative hypothesis is true, given that I have a significant result? So it's a bit of a weird thing to ask, because you have to think of a hypothesis in terms of random things. So it's a bit of or at least like a large set of hypotheses, and you're thinking, okay, I'm going to take that alternative hypothesis and thinking, okay, what's the probability that it is true? So it's a bit of a you have to change a bit of your set of mind if you are usually using hypotheses as non-random things. But in that case, we're going to say, okay, there are many alternative hypotheses possible, and some of them are true and some of them are not, right? And this is the mindset that we are taking. So I'm going to try in the next 5-10 minutes. So bear with me. It's going to be a little bit maybe not that easy, but I'm going to try to tell you what is the positive predictive value. How do you derive the positive predictive value from simple statistical principles? And the first thing that I would like you to show to see is that let's say you have also the probability of the test being significant is just the probability of the test being significant, and we are under the alternative, plus the probability of the test being significant, and we are under H0. I mean that sounds simple in a sense, because we are either on the alternative or the null hypothesis. Right? There's no overlap. It's two different independent events. Now, so remember that's we can write that probability as the sum of those two things, one under the null, one under the alternative. And then you probably all know the Bayes theorem, and that's very famous. So, which states that the probability of the two events A and B is the probability of A knowing B times the probability of B, right? And then if you rearrange things, you can compute the probability of A knowing B or the probability of B knowing A, with these probabilities, these marginals, the conditionals. So, and there's a nice little explanation of what is the Bayes theorem here. So if you like, let's say you have some spam. Let's say you have in the spam the word free lunch. It used to be some other word, but anyways. And then the events that are both the spam and there's a word free lunch are the intersection. And then the probability of A. So let's say spam, knowing that we have free lunch in the text of the email, is just normalized by the probability of the free lunch. So this area. So it's just normalization. So it's the probability of the two events normalized by the probability of the of one. And you can write it again using the conditionals here. So you can think a bit of that Bayes theorem. It's not that too complicated to understand using this kind of graphics and the Venn diagrams. So now you can apply that to our question. So we've seen the probability of the test being significant, all right, and we can write that probability using the Bayes theorem, using so probability of the test being significant and HA. And the alternative, and that's probability of test significant, knowing that we are under HA times the probability of HA, and the same thing for the null, for the probability under the null. So that's easy. So the probability of HA, knowing that we are under a test that is significant, we just rewrite with the Bayes theorem, and that's easy as well. And then we expand the normalization term here, which is the probability of the test being significant, as we've seen before, like using the. Okay, so we seem to have a complex formula here, right? But all those elements were kind of easy. Right? There was no very hard, complicated. It's just like replacing with a simple the Bayes theorem, this addition of those two probabilities, and that's it. And you've replaced those things in that formula, and that's basically it. So now I think if you go back to that document, if you read carefully those lines, you yourself will be able to derive that. It's not far away. All right. So now we look at that sort of a big term here. So we got the probability of the test being significant on the HF times the probability of HA. But the probability of the test being significant on the HA, it's obviously 1 minus the probability of the test being non-significant on the HA, and that's our power, right? So we've got that term, we know that term. And then the probability of, so if we rewrite this, we have this easy formula. So now we have something which looks like the power times the probability of HA divided by the power times the probability of HA plus alpha 0, the risk of error, and because that's here, that term here is the probability of the test being significant under H0, right? So that's easy. And now if you, we have simplified that very much. We've got the power, we've got alpha, and then we've got the probability of HA and the probability of H0. So if we just divide, if we take the odd ratio, so let's say we have a probability of H0 divided by the probability of HA divided by H0. So that's the odd ratio. So that's the ratio of how likely the hypothesis that you are testing is going to be true compared to the null, right? So that probability, sometimes you are testing something which is a bit unlikely, and that ratio should be small. And sometimes you're going to test something that is fairly likely, and that ratio is going to be large, right? So that's what the classical odd ratio that you probably have seen somewhere in some publications already. So now we have a very simple formula. The probability of HA being true, knowing that the test is significant, is power multiplied by the odd ratio divided by power multiplied by odd ratio plus alpha. So now you can think of that formula. And again, there was very little derivation before, right? It was a very simple sort of like a derivation. Now we can think of that formula. What's happening? When is that number going to be small, and when is that number going to be big? If alpha is very, very small compared to that product, the W times R, to the rod ratio. Then if we have that, then the probability of HA, knowing that the test significance is going to be high, is going to be close to 1, right? But if alpha is kind of a small compared to this product, then obviously this probability is going to go down. So it's really a question of what is my risk of error of type 1 compared to something which is the product of the power and the odd ratio, right? That's it's kind of amazing with like a simple statistical principles and with so Bayes theorem, using like a very simple statistics, then you get that. I think that's a very interesting formula. So now, so how do we? I think the exercise now that I would like you to do is, can you go in your the preferred tool? It could be R if you are you're happy with R. It could be some other things. And I wanted you to actually implement that little formula and see what's happening when you have low power and when you have low odd ratio, and what's happening when the alpha is going to change. So given that the time is a bit tough, I'm just going to show you what it looks like in the notebook. So let me run that notebook. So this is just to show again the same thing. It's a bit more developed, but it's easy. So this is here a simple function to compute the positive predictive value. Okay. And then a simple function to display things. And then I was going to take the example from Button et al. I think it was 2013, estimating the power of studies in neuroscience and showing that the average or the median power in neuroscience is actually between 0.3 and 0.4. I think that was the result of Button et al. They looked at all those meta-analyses and looked at the power of the actual analysis inside those meta-analyses, and they found out that the power was I think if someone remembers, tell me, but I think it was 0.3 or 0.4. It was the median power. So basically, there are 50% of the analyses being done in neuroscience that have less than 0.4 power. So power was found to be very, very small in general. So let's take some examples. So let's say we have an odd ratio of 1/5. So it means that the probability of the alternative is maybe something like 20% compared to the probability of the null. So it's not it's a not very likely hypothesis, but it's not a very unlikely hypothesis. So it's something which may be very interesting to test, right? And then let's say that our power is just maybe 0.5, or let's say take the example of Button et al. And then our alpha is usually 0.45 alpha, right? So with that odd ratio, with that power, and with that alpha, we've got the probability of the alternative to be true, given that we have a significant result, a significant test, is about 0.6. So about 2/3. We have 2/3 of a chance that the alternative is basically true. But 2/3, 1/3, it's not a great number, right? It means that there's going to be if those numbers are correct, it means that 30% of the publications are going to be describing results that are probably not true. So now, if you vary the power, let's say 0.4 is actually it's optimistic. There's actually half of the studies that have a power of less than that. So let's vary the power between and let's look at what with the same make sure that I take the same parameters. So power is varying. This is a little bit of a, so maybe the odd ratio is 0.2. So let's make it, okay. So with an odd ratio of 0.2, with an alpha of 0.05, and this is what the positive predictive value would look like. So if you have like a very low power, but 0.2, 0.3, there's half a chance that your hypothesis is going to be untrue, even though your test is significant. And in the same way, you can look at varying the odd ratio, of course. See if your hypothesis is actually very unlikely with a power of 0.4, 0.5. Let's say here in this example, let's take the median of Button et al. And then this is going to be the what you get from the curve. So basically, with an odd ratio of an unlikely hypothesis, again, you get the 2/3 of a chance with that the hypothesis is untrue. And the last thing the last number that can vary in that formula obviously is the risk of error. And if you look at this risk of error and you vary that risk of error again with the power of maybe 0.5, then with a 0.05, you also have like this kind of a number, the sort of not too great probability of the alternative being true. The problem with that sort of analysis, first of all, there are several problems. First of all, it's very hard to estimate the odd ratio. So let's say you're trying to test whether the hippocampus of the size of the hippocampus is linked to maybe gender or age. How do you estimate whether that hypothesis is actually unlikely or not compared to the fact that it's not linked? So that's one problem. I think it's although it's hard, it's also useful to look at the range of things or a range of estimation and say, okay, I don't have a good number, but I can actually look at whether if that was a very unlikely hypothesis, what kind of a result I would get for the PPV, and if I was a likely hypothesis, what would be the number? So I think looking at those range of numbers is actually better than not having any information. I mean, that's one thing. The second thing is that I've taken alpha equal 0.05. I mean, one could say, oh, but our alphas are much less than that, and that's possible, but that's something that you have to decide in advance, of course. And there's also a bunch of, a large number of people that are trying to push the idea that we should take a more restricted alpha, but at the same time, we know that it's very easy to do some kind of p-hacking, even if you don't want to, like even if it's not like something that you are really aware of. It's just by thinking, oh, I should maybe try to include that variable, or maybe I should select only those subjects that are those characteristics or those things, and we know that this kind of practice that are just like seems a bit not too dangerous when you do them. And we know that they are inflating the risk of error quite heavily. So if you look at the Simonson and Simon paper, or like if you can see that those practices are actually changing the p-values, the risk of error of type 1, which fairly heavily. So let's say the p-value is not 0.5, maybe the p-value actually that is seen in most study could be something which is around 0.2, 0.3, even more. In that case, that sort of a number, the probability of that hypothesis to be true, even though the test is significant, can go very low. So I think it's just a nice tool. To think, okay, the important result is not whether my test is significant. That's not the important result. The important result is whether the probability that the hypothesis that the alternative hypothesis is likely to be true or not. And that depends on those 3 parameters: the risk of the type 1 error risk, the power, and the likely, and how likely is the hypothesis to be true compared to the null, the prior of that. So I think I will finish that. When is the actual end of the? Is it 4 o'clock or is it 4:30? I can't remember. That's past 4. But we need 10 or 15 minutes to wrap up, right? Okay. Okay. So the second. So any question on the PPV on the positive predictive value? Yeah, sure.
So my question is, what's the practical advice then for neuroimagers? Like, what should we be taking away from this when we're either designing our studies or selecting a sample size? Or, well, obviously, the more the better, but...
Right. Well, I mean, the practical advice is first, do I have a reasonable range of prior or like an odd ratio? I mean, if I'm, it's basically forcing yourself to define your hypothesis very precisely, and forcing yourself to think about the likelihood of that hypothesis, the prior compared to the null. And if you think, okay, maybe there's half and half chance, or maybe that's or I really don't know. I need to look at all the range, okay. And then you're forcing yourself as well to think about power. Okay, I don't really know the prior on those things, but maybe I've seen some kind of similar studies, and those studies have found some effect size with that sort of number. And sure, I'm not looking exactly at the same thing, but it gives me some idea of what sort of effect size I might be expecting. And again, it's just forcing yourself to try to put some numbers, try to get some first estimate, even if they're off, having and varying those things to see what's the impact on the positive predictive value. And also to think that not take. I mean, like we still basically a lot take for granted the result that we find in papers. So instead of thinking, okay, that's a significant result, so the hypothesis, the alternative hypothesis is likely to be true. Say no. I mean, the hypothesis is not necessarily likely to be true. It depends on power. It depends on the prior.
Yeah, I'm just going to add to the same thing. We often finish with a p-value and say, oh, the p-value is significant, and therefore I'm happy, and walk away. But the p-value being significant is not the end of the story. The end of the story is whether the alternative hypothesis is really true, and that's what this is. And we don't think about it nearly enough. Well, that's what we really want to know. Have I actually found a true association here? What's the probability that I found a true association? And so this is a far more important parameter, or a far more important result, and we rarely think about it.
Yeah. Yeah. So basically, I think the most important aspect of that is make you think about it. It's and also try to get some value in the literature that would support or not the hypothesis that you're testing. One of the problems, of course, is that there is a tendency for any scientist who has a theory to sort of cherry pick those papers that are promoting or supporting the theory. That's one of the problem. The other aspect is with small power, when you're getting published, it means that you have a significant p-value, because that's the culture in the scientific community at the moment. And a small power means that if you're being published, it probably means that the effect size is very inflated. So if you're only selecting those low-powered studies that are significant, you're going to have a very large inflation of the effect size. So you're probably going to estimate that you are likely to find some result. I mean, you're going to overestimate your power. You're going to overestimate the effect sizes, and so that's another a problem that we have to think about. But yeah. Yeah. All right. So the last thing I wanted to show you briefly, and that's something you can play with, and I'm not going to, is another little notebook somewhere. So taking the same data set as Celia has taken and working in Python rather than R, but so that you have like a. I'm just going to read using pandas to read the CSV file, and then maybe you want to make sure that your data set have you remove all the null and the none of the data set, so you're looking at what's there in terms of a data set, and then some basic statistics and so those things. Those things are really important to when you start to work on data sets. You really have to sort of do the graphs that you've seen that Celia has done, or do check all the have all the means of checking that your data are actually correct. I mean, so you have to look at is there a crazy number somewhere? You have to look at outliers. You have to look at missing data, all those things. I mean, preparing the data set such that you're sure that you're not going to use some crazy data or or do some mistakes is completely key. And sometimes, so here I'm dropping the non-numerical value, and I'm looking at the formula using Python. So I'm going to regress the left hippocampus with age, site, gender, and some new variables and the mystery variable that Celia created. So I'm regressing these things, and then I'm going to use the whole data set for that thing. So I've got almost 1,000 subjects. I had to drop 3 because of the missing values and things like that. And then the regression formula would be simple. I mean, my left hippocampus is just a linear model of age, site, gender, those variables. And then I fit the model using a stats model here, and then looking at the p-value for the edge. What is there an association between the hippocampus volume and the edge? I don't find any association here. Now, if I say, oh, but those mystery and new variables that have been there, I don't know. I mean, are they really important? I've just put those things in the model, but I don't really probably don't need those things. And then if you look at the result of that, if you just recompute your model with like a different set of variables, and in some studies you have like tens or possibly hundreds of variables, right? And then you'll find a very, very different p-value, of course, and that is because some of those variables were linked to age, for instance. So if you have some correlation in the model, of course, you're going to remove a lot of the variance due to that correlation. So I was going to show you the Steve's Shiny App thing, and that maybe it's just a nice way of illustrating that problem. So where is that thing again? So in that little app, all those variables, and this is using the ping data set. And what we've done here is to look at all the models that are with all the looking at the gender coefficient compared to on the I think it is the hippocampal volume as well, right? So looking at the effect of the gender coefficient on the hippocampal volume, I've got like a bunch of variables that are being collected in this study. I don't know which ones are actually useful or not, and I'm not too sure. So I'm going to make all the models, all the possible models with all those variables, and this is how you can look at, okay, if I remove, I shouldn't remove text because that's the actual thing that is tested. But if I remove some of those other variables, what is happening to the model fit first, and what is happening to the effect of the effect size that I found here? So in this instance, I find that there's a lot of models that I find almost like a null effect, and there's a lot of models that are found that are in effect of about 500 milliliter for the change in hippocampal volume between the two populations, between the genders. And that obviously is because when you remove, for instance, those variables that are accounting for the brain volume, then you left with this effect size that is big, and that's because obviously there's a confound variable that you're not accounting for properly, and that confound variable is eating a lot of the variance and therefore of the effect size. So what's interesting here is that you could think of one of the problems that we should think about is we're collecting those variables. We don't actually know, we don't have a clear idea of which one are going to be related to the effect that we are looking at. It's not very clear, right? We could collect some other things, and then suddenly we realize that those things are very related to the effect that we are estimating, and therefore this vibration effect on the collection. So the only way this is going to be useful in the long term is if we accumulate those results, looking at all those variables that have been included or not in and this is the only way we can sort of solidify the results, is to make sure that we increase the number of things that we can test, and we get a clearer picture, which means that we have to collaborate with many labs and and get much bigger set of data, and also a deeper phenotyping aspect. Otherwise, we are going to probably get some wrong results. And we are already, but so that's just a little thing that helps to think about this problem. How variable these effects are.
JB?
Yeah.
I want to add in here. So in the reproducible research context, right, if you look at the cloud of points there, either the top or the bottom, you have quite a large range of the estimates for the sex effect. If you fit all of those models and then you report the best one, of course you're introducing a substantial bias, right? By reporting only the best one, you have almost by definition picked a biased result. So when it comes back to recording your scripts, right, you have to record inside your whole history of the analysis the fact that you looked at all of these 55 models and picked the best one, so that anybody who wants to understand the bias that you may have or understand the analysis that you have knows that you looked at 55 models and picked the best one.
Right. And there are some model selection procedures, of course, that will tell you, all those models are relatively equivalent, and maybe those ones are actually much better than others, and there's a large literature on that problem, of course. But basically, being aware of the fact that when we're exploring data, we should really be exploring data on data sets that are separate from the data from the data set that we're actually testing some proper hypotheses. So splitting the data, making sure that there are some data where you actually haven't touched, or trying to replicate on another cohort that is going to be slightly different, of course, and see how that result generalizes is the right way of doing, but it's just much more costly. So I think we should have less studies, but more powered studies, and more carefully, and with many more variables and many more sort of checks on the models. I think that's all that I wanted to say. Is there any other question on this? Yeah, please.
Kind of bootstrap really helped In your opinion, would you say that the bootstrapping would help alleviate some of the problem we're reporting? And is there any mechanism within DataLab or other software, FSL, etc., that actually help with that?
So I don't think there is a mechanism to do specifically bootstrap in DataLab, but you certainly can. Let's say you have a script that would do some bootstrap and would look at what's the effect. So bootstrap will be looking at the some effect of sampling within your sample. Can I what's will be the vibration effect due to the sampling within that cohort, right? I don't think there's something specific in DataLab, but certainly you can use this to actually show what is the sampling vibration that you get from and that's already useful, because that's showing more information that's just showing one point. You're actually looking at estimating a bit of the variability of your results using Bootstrap. So definitely yes, Bootstrap if you can, because sometimes you have to do some jackknife rather than Bootstrap. But yes, using the resampling techniques is really important to have some ideas of how stable the result is compared to the sampling. It doesn't go up to getting another cohort and looking at the results on another cohort, and it doesn't do that. So you may very well still be like a bias by the specific cohort that you're looking at, but it's certainly a good thing to do. Yeah, it's costly because sometimes sometimes it is costly computationally, but it's yeah.
Just 2 comments. One on Celia, right? Yeah. Yeah, so what you mentioned about selecting the best, you obviously mean the best model, right? The best R squared, not the best result, correct?
Yeah, best R squared. I guess I'm kind of saying, you say, I think I like this dot, This one has the strongest effective sex. This is the strongest association with my covariate that I like. I'm going to keep that dot. And then obviously that's going to introduce a bias for the effective sex. So your bootstrap or anything like that will allow you to really look at the variability.
Yeah, so to answer this, so I'd say, well, obviously we should never do that, right? Absolutely, yeah. So it's as obvious as it may seem, it's never enough to repeat that we should never do such a thing, right? And then commenting on the follow-up question on this and about tools available, and JB mentioned resampling methods in general, and actually, as a matter of fact, FSL has a tool that can do something related to this, which is a tool that I have written, right?
Oh,
it's
nice.
Palm, yes. And specifically for this data set that you're showing here, for this example, it would address precisely this situation. So you could run, so you have your subjects, in this case 997, if I understood right, after excluding 3, and then you have many different models that you would like to try on those same subjects. So what you can do is you enter your independent variable as your input data. You enter all your models, however many you may have, can even be hundreds. Your computer is the limit, however much memory or computational power you have. And you indicate, you pass a flag. It's a permutation test, so it's a resampling method, therefore related to Bootstrap. And what you have to do is you have to pass a flag telling that you want to correct across all those models that you want. And there is no magic to this. The correction is based on the distribution of the maximum statistic, which is the same correction that we already use to correct across multiple voxels, right? Use the distribution of the maximum across all the voxels in the brain. So in this case, we would use across all the models. So after building the empirical distribution of the maximum across all the models, we get the p-value for all the models, correcting for the fact that you have looked into potentially hundreds of them. And the flag in this case, it's core-con, for correction over multiple contrasts, which encapsulates multiple contrasts within a model and also multiple contrasts across multiple models. Right?
Yeah, that's interesting. Like so in this instance, for instance, you have 2 to the power of the number of variables model, and that's and you could circle all those through, and then as you say, get the maximum or the minimum p-value in that instance, and then see whether under permutation that you find the distribution for that minimum p-value and so on. At the same time, some of those models should probably be rejected just on the basis of the so that distribution maybe may not be like I don't know what the effect of it would have, but it is possible that we should have something that says, oh, all right, so that variable certainly have some effect. It should be included in the model, and in that specific instance, we know that we should include the total brain volume and that's. But showing the vibration effect and estimating the probability on that vibration effect, I think it's a very interesting approach. Great.
Yeah, it wouldn't tell specifically which variable should or should not be, but you can tell at the end, you can say, right. I looked into however many models I tried, with or without some procedure for variable selection, and you can give a p-value that says, yes, that's my correct p-value after I have looked into all this. And it doesn't require independence between the models, so you can repeat variables. Right?
Sure, it's a permutation.
All the models they have some degree of no independence, right? So that would accommodate that.
Thank you. So I think we need to move on. And I think Nina, you are wrapping up, and yeah.
So first of all, we want to say thank you for attending today. I have a link above here. You also have in an email that I sent to you a few minutes ago. If it's easier to just click on the link. We wanted to take some time now to get immediate feedback from you so that we can know how people moved along the continuum of learning today, and be frank and be brutal, please, in your feedback, because you're our lab rats today. And we want to improve what we're doing here. We want to tailor it to different audiences with different knowledge bases, and so this information helps us. So I'm just going to stay quiet for about 5 minutes while you all go into your email or bring the URL up, and then we can touch base about that in a few minutes. Yeah, the bit.ly URL, or it should be an email that says something like link, first word, link to OHBM survey. So far we have 13 responses, so we're getting close. In the interim, I wanted to say the gentleman that was speaking about his software, I was interested, so I went to the nitric.org website and I Googled on nitric in our search Palm, and I realized, wow, he's got the software there, he's got the link to his GitHub. He updated it in April. His name is Anderson Wilker or Walker or something like that, so I knew exactly what he was talking about. So that's my shameless plug for the Nitric website, which each of you all should have received a page on. We'll be in booth 10, and we have lots of candy, and we get bored. So to the extent you can swing by and visit, we have data to share and a lot of information to share, and would love your feedback on our redesign. The same team that is behind ReproNem is most of the same team behind Nitric. So there's a lot of connections between the two. So we'll just go ahead now, since we have already 15 responses and some folks have left. And just for fun, we're just going to show the slides, the questions side by side, your responses, so you can see the difference. Since I can't read over there, I'll just come over here. So the one question we didn't ask before was whether you had problems downloading the course materials before. That'll give us some information on how to make that easier in the future. So if we could just scroll down on the next one to make it even. All right. So, well, we did move some people along the continuum on the first one. I'm not a statistician, so we're just going to scroll through these quickly, and you can visualize them and make your own assumptions from this, and critique the survey questions afterwards to see if they were biased or not. But I do see that we did move people along the continuum for the motivations, and we got some comments there. Let's go to fair data. And, well, again, improvements here, although I'm a little concerned because the one person that thought they were very familiar is not. But I don't know, we've got different respondees on each of these, so we can't exactly compare it one-to-one. We've taken a lot of notes about issues and questions that people brought up, and we'll be using those notes to improve things in the future. Also, all the presentations and additional information is on GitHub. I'll be sending an email link out to everybody with the link to that GitHub. There's a question?
Yes. Is before on the right or the left?
Oh, yeah. Gee. Okay. The new one is the one on the left. I was going to say, that's really bad. We're swimming backwards. Can you switch it? It doesn't work with my brain if I don't see it that way. Okay, better. Better. Okay, number 2. Good. A lot less responses on this one. But I'm not too happy about this. We'll have to read through all the comments. Let's keep going. This one looks a lot healthier. Let's keep going. I'm going to leave this to you to draw your own conclusions. For those of you who haven't completed the survey, please make sure to do so because we had a lot more responses initially. And then conclusion. This is the big one. Okay. Okay. Hopefully there's some of you that are just taking more time to complete the survey that'll skew it a little bit more to the right. All right. Does anyone have any additional questions that you want to ask before taking off today, other than us providing you access to additional information like this on GitHub and the presentations? David, did you want to make any concluding comments, or JB?
I just hope it's been useful, and you had some kind of fun in some ways, and really we value your feedback. If you think you realize that there's so much that has been presented, there's really a very large body of knowledge that has been presented. So even if you just grab maybe 20% or 30% of that, I think it's already a good step. And even if you just now have a very a greater awareness of all the problems, the potential problems, and awareness of the tools that you can use for mending those things, those problems. I think that's already I think we should be already happy with that that outcome. I think please interact on GitHub on the course. All the material is on GitHub, and you can raise issues and say, hey, this is not very clear, or what was the section on that problem, and so on. So you can we can collaboratively continue to develop those materials. I think to us it's been very, very instructive. I don't think you are the only one who have learned things. We have learned a lot as well. We have different backgrounds and different. It's been really good, and thank you. And as well, I think it's a question of whether that kind of experiment is something that we should pursue in the future at this conference. Something which is going away from the traditional presentation to the actual hands-on is much more challenging. It's much more difficult. But the question, I think, you have to tell us whether that's worthwhile doing and pursuing.
And my only echoing is that hopefully if you found any of these tantalizing that you do need to know more, there is much more information to be learned, as we encourage you to continue the education on this. And also just to remind one more time that this train-the-trainer type of idea, that you guys are encouraged to finish those courses and then to help us spread the news to others and do your own trainings. And again, we're all into helping you do that, and there's certificates and things like that we can help work on. And again, we need to get you guys taught, and you guys need to teach a few people, and we really want to encourage that. And so thank you for attending, and thank you for keeping attentive to this topic as you go forward. Thank you all.
Remark?
One last thing. I know people were perhaps at different stages with getting things running, not running. If you have any questions, that GitHub repo that you saw, the OHBM training, there's an issue tracker there. Feel very free to submit issues over there, and we will help you out remotely or elsewhere to fix things up.
Thank you again. Have a great conference and a great evening. And hopefully see you next time.